Presentation and experimental assessment of a thermal energy storage unit using sunflower oil that can be integrated into a solar cooker. My name is Pauline Bala. There are different types of solar cookers that can be used directly to harness solar radiation, such as parabolic solar cookers, solar cookit, and box solar cookers that are typically found in Kenyan context. However, these types of solar cookers have a limitation of their inability to be used beyond sunshine duration, making solar cooking practice less attractive and unreliable for majority of the population wishing to take it up. So is there a solution to this problem? Different studies have looked into possibility of integrating simple but low-cost thermal energy storage unit into solar cookers. This is to extend their duration of use past the sunshine available period. For instance, sunflower oil has been proposed for its less toxic food-grade nature as a suitable thermal material following its favorable thermophysical properties to store thermal energy for later use. Sunflower oil has been tested with a simple energy storage model that also serves as a cooking pot but is double-walled. This unit has been tested in South African context through experimental studies. Further, similar design has been tested in Uganda under laboratory settings in comparison with other vegetable oil as a thermal material. These studies have indicated the high potential of sunflower oil as a candidate material to store thermal energy harnessed by the sun. However, there are limitations to discharging the stored energy to the cooking vessel because of low heat transfer and thermal conductivity to the cooking vessel. To improve on this limitation, this study focused on testing a simpler cylindrical container filled with sunflower oil. The unit can serve as a hot plate when it is heated on a solar cooker during the charging phase. It can then be discharged when offloaded past sunshine period and be used for cooking when cooking pot is directly placed on top of it. To test this, the study estimates the total energy stored in the unit containing oil, determines heat retention potential, and its heat utilization efficiency. The experimental setup of the thermal energy storage unit was tested in a laboratory setting in Belgium first, with an electric heater used for heat supply to simulate a parabolic solar cooker in real life. In the field setting, however, the parabolic solar cooker was used. In the field setting, the unit filled with sunflower oil was placed on a parabolic solar cooker for heating during the charging phase and offloaded after heating during the discharge phase to enable heat discharge into a cooking pot placed on top of it while keeping the unit in the pot insulated. Temperatures were monitored by placing thermocouples at different oil depth levels during the charging and the discharging phase. Another temperature readings were made for the water inside the cooking pot and the ambient temperatures were taken. The field experiment was tested in western part of Kenya near Lake Victoria on a suitable sunny day in October 2024 when the average solar radiation was 518 watts per meter squared and the ambient temperature was 28 degrees Celsius average when the ambient condition was generally less windy. Results indicate that during charging, two peaks of high temperatures of the oil was recorded, with the first peak of 137 degrees Celsius only after 30 minutes into charging, with little solar intermittence, and the next peak higher The next higher peak recorded 3.5 hours into charging with a temperature of 161 degrees Celsius. There was a significant decline in the temperature trends before the second peak, which can partly be explained by the intermittent pattern of solar radiation as indicated in the graph on the right, but could be largely associated with non-ambient factors in the delays to adjust the parabolic cooker to align well with the direction of the sun. Sunflower oil. On heat retention for the sunflower oil was able to retain heat above 90 degrees Celsius for over 2 hours in both the lab and field settings of the experiment. The rate of decay during the cooling was estimated to be 0.004 degrees Celsius per minute, with over 2 hours of cooking temperatures above 90 degrees Celsius sustained. It can be interpreted that it is possible to cook low heat demanding food that can cook at low temperatures but slowly through simmering with this thermal energy storage. This may form a basis for future cooking trial. With a maximum temperature of 161 degrees Celsius attained during charging in the field, the total energy stored by the sunflower oil was estimated at 894 degrees Celsius after 3.5 hours of charging. From these, only half, about 47.7% of the energy stored was released by the oil during the discharge phase. However, the utilization efficiency of the boiling water was estimated to be only 11.7% of the energy released, enabling an increase in the temperature of water only up to 51 degrees Celsius. This was low but comparable with past studies by Mawere that tested a similar material for cooking potential. The low utilization efficiency can however be explained partly by the high specific heat capacity of water, may also be attributed partly to the heat loss from the lid, the cooking pot that remained uninsulated during the discharge, and may partly be explained by the low thermal conductivity of the sunflower oil to release energy. The low utilization efficiency may again be explained by the inefficient contact between the thermal material and the unit as well as the cooking pot. In conclusion, sunflower oil in the improved simple thermal energy storage unit attained high temperature with an equivalent energy of 894 kilojoules stored after 3.5 hours of charging in the field setting. Favorable cooking temperature above 90 degrees Celsius was sustained for over 2 hours during the discharging phase of the unit containing heated oil, but a low utilization efficiency of 11.7 was recorded by the loaded water placed on top of the unit. This only led to a temperature rise of 51 degrees Celsius. We recommend other thermal materials with higher heat storage capacity and conductivity be tested with a similar model. We also recommend that with this setup, a simmering cooking experiment conducted with food of low specific heat capacity. And thirdly, we recommend that the performance of the model could be enhanced by improving the contact between the oil and the cooking vessel to enhance heat conduction and enable cooking. Thank you, and I wish to acknowledge the support that I have received from different organizations as shown below. Thank you.